Okay, so we would like to use the Green-Stokes formula in order to compute this vector line integral. The truth is that we're not using the Green-Stokes formula for the computation. We use the Green-Stokes formula in order to translate this vector line integral into a vector surface integral that we will then compute. So the Green-Stokes formula is not a computational tool, it's a translation tool. But in any case, first of all, let's understand what the path of integration is here. So we have these points 1, 0, 0, 0, 1, 0, and 0, 0, 1. And we're being told that they're traversed in this order, in the order that they're listed. Maybe it's not so clear from the statement, but this is what is really meant here. And in order to apply the Green-Stokes formula, we need to choose the right orientation for the surface patch, which is the interior of this triangle. And you can easily see from the picture that it's the upward orientation, because if you stand on the boundary in the upward orientation, meaning having chosen the upward normal, and you're facing the boundary in the direction that it's traversed, then the domain lies on your left, which means that this is the compatible orientation. So let's begin by identifying the underlying vector field. So whatever is sitting in front of dx is the first component, whatever is sitting in front of dy is the second component, whatever is sitting in front of dz is the third component. And you can see that the differentials have been listed in an unusual way in this vector line integral, but that's exactly what this should be. And then we want to take the curl of this vector field, and this is formally the cross product of the gradient operator with f, and this is going to be I, j, k, and then we have the differentiation with respect to x, with respect to y, with respect to z, and we just put the components. And now let's see what we're getting here. So delete the first row, delete the first column, and you will get the derivative of x with respect to y minus the derivative of x squared with respect to z. Both of them are 0. Then delete the first row and the second column, and you will get the derivative of x with respect to x, that's 1, minus the derivative of negative y with respect to z. But remember, it's the middle one, so you will put a negative 1 here instead of 1. And finally, delete the first row and the third column, and you will get the derivative of x with respect to, of x squared with respect to x, that's 2x, minus the derivative of negative y with respect to y, which is minus 1. So minus 1 will give you plus 1, and that's the curl. Okay, now we need to parameterize the surface patch, and the idea here is very simple. I mean, this is part of the plane x plus y plus z is equal to 1 by the equation of the intercepts. This can be considered easily as a graph. And this means that we can consider a graph parameterization g of uv equals to u comma v comma 1 minus u minus v. And it's important to identify the domain of this parameterization. Every time we talk about a graph, then the domain is really the projection of the graph onto the xy plane. And so here, this is going to be, the domain is going to be d equals to all the uv's such that v is greater than or equal to 0 and is less than or equal to 1 minus u, and u is between 0 and 1. And by giving this description, we pretty much determine how the final integration is going to be carried out. But we have a few more steps to take before we get there. So first of all, we need to find the normal vector of this parameterization, and this will be the cross product of those tangent vector, g sub u cross g sub v. and this is going to be ijk, and we will have 1, 0, -1, and 0, 1, -1. What we find by taking this cross product is 1, 1, 1. And since this is positive, we will have that this is greater than 0. I'm sorry, this is the chosen normal. So this subscribes to the orientation that has been chosen. So we're good. Okay, so then we want to compose the curl of f with the parameterization. So this means that we should take the curl of f, and everywhere we see an x, replace it by u. Everywhere we see a y, replace it by v. Everywhere we see a z, replace it by 1 minus u minus v. And of course, this will be 0, -1, and 2u plus 1. And we reached the final point. So let us here state that the Green-Stokes formula tells us that the vector line integral of a vector field f along the boundary of a surface patch is equal to the vector surface integral of f. It's the flux integral where we take the orientation of the by the compatible normal. Okay, so sometimes this integral can also be seen to be written like this. Okay, but in any case, we will use this notation. And this is what we're computing right now. Oops, sorry about this. Obviously, I made a mistake. This should be the curl of f, not f. Of course, there's a differentiation that happens here. And let's make sure we put it here. And that's why we've been computing, obviously, the curl. Okay, so now it's the correct thing. Okay, so let's finish the computation. So now things should be straightforward. Let's compute the dot product of the curl with the normal vector. So this will be 0, -1, 2u plus 1 dot 1, 1, 1, which is going to simply, that's -1, which is simply going to give us 2u. Okay, so finally we need to integrate this to u first with respect to v from 0 to 1 minus u, and then with respect to u from 0 to 1. That should be a pretty straightforward computation. So this gives us 2uv from 0 to 1 minus u and 0 to 1 du. So this is going to be 0 to 1 2u 1 minus u du, which is 2u minus 2u squared from 0 to 1 du. So this will give us u squared minus u cubed, or 2u cubed over 3 from 0 to 1 equal to 1 minus 2/3, which will give us 1/3. Let's double check, make sure there is no mistake here. It looks good to me. And that's it. Okay, so this is a long computation, and to sum up things, we need to know our Green-Stokes formula. And then we need to know what is entailed in computing this integral, which means to find the curl, find a parameterization, and then compute the vector surface integral of the curl using that parameterization. And that's all. Thanks for watching.